candidate for the seminar?
Yeah.
All right. All right, project leaders and other types.
Other types. What kind of type is that?
All right, thanks for joining us on this off day for NAIA seminar. It's my real treat to actually introduce Nick Obradovich. Nick has got his PhD from, when did you get it? Okay, just a couple of years ago, great, with James Fowler down in San Diego, UC San Diego. And Nick is actually following his advisor's footsteps. He's actually been interdisciplinary researcher. So Nick's PhD is in political science, but his work also has to deal with computational social science. It will have to elements of causal modeling, which I look forward to hearing, and also addressing, of course, also political and policy issues about how climate change can influence and affect people's behaviors. And I should also mention that Nick is now doing a postdoc in MIT with some of my former collaborators, Manuel Cebrian and Mr. Bambora, and please join me in welcoming Mr. Isaac.
Thank you. Thank you all for being here today. I appreciate it. And what we're going to do today is talk about weather and emotions. And in order to talk about that, I'll start with a little bit of background about how I got interested in this question in the first place. I'm really interested in climate change, very broadly conceived. And as you all know, the Earth is warming, and the warming rate over the last couple of decades has been accelerating. And it's likely, given the course of historical emissions trajectories as well as future emissions trajectories, that we are headed to a world that continues to warm over the course of our lifetime. Global mean surface temperature increasing over the course of our lifetime. And what I want to know is, given that many natural scientists have thought about the effects of climate change on natural systems and are continuing to do that research, what might be the social system impacts of climate change? What might happen to our social systems broadly conceived? Just turn up the dial on the complex system that we live in. In order to answer this question precisely, you need to know the answer to whether or not weather and climate causally affect that social system. And it sounds kind of basic, but it's actually a really tough question to answer empirically. There are kind of obvious large-scale impacts that we know are likely to follow from the natural system impacts of climate change. Crop losses in places that are traditional breadbaskets, sea level rise due to ocean warming. Resource conflict is a literature emerging from this, suggesting that the increasing constraints on our resources might lead to state conflict, and also potentially non-temperature related ecological losses and then subsequent food system losses due to fisheries collapsing due to ocean acidification. And these have been talked about pretty extensively. You've probably all heard all of these things. But there are ways that we rely on our climatic systems and the meteorological systems they produce that are more day-to-day. They're less extreme. They're kind of more normal. And the question is, what happens to us when those systems change a little bit over time? And if you aggregate over space and time, and you think that we are affected by our climates on a daily basis, then the cumulative effects of all of that could end up being somewhat large. So that's the Yeah, go ahead.
What about natural disasters? That seems to be something that comes up a lot.
There are many potential large scale. So natural disasters, shocks, increased frequency and intensity of hurricanes, increased intensity of tornado days in the American Tornado Alley. All of these things are likely effects as well. I didn't mean for this to be an exhaustive list by any means. And so myself and others working in this somewhat emergent field have done a good amount of research and found that we do depend causally in myriad different ways on our climatic system and on the meteorological systems and the weather that we experience. For example, researchers have found that exposure to heat stress harms human physiological load. It increases rates of fatigue, it reduces the efficacy and duration of sleep. We actually were one of the groups that produced the sleep-related results in a paper in Science Advances. We found that exposure to unusually warm temperatures during the summer nighttime temperatures during the summer reduced people's self-reported sleep quality. And interestingly,
There's a song by Ella Fitzgerald about that, isn't there?
it's
Still darn hot.
exactly. There are, and this is a really good point that we'll get back to, but there are lots of kind of cultural and normative ideas around the way that weather affects us. But many of these questions haven't been answered rigorously or empirically yet. So we looked at sleep, and this was self-reported sleep from the United States, a representative survey of 100,000 people. But it's self-reported. And so we thought, well, okay, one way to actually see if this holds up in the real world is to get actual measures of sleep duration. And so we used actigraph data, Fitbit data, to see whether or not people's nighttime sleep was indeed interrupted by unusual temperatures. Go ahead.
So the unusual temperature here is related to their location, I would assume.
I see where you're going with that. We'll go right into that. And then after I go through the methods, you still have that question. So the functional form we uncovered with the actigraph data looks basically identical to what we uncovered with the self-report data, which is always really nice if you extend your results in the functional form. Same. We also did research on physical activity rates and the degree to which people engage in recreational physical activity as a function of the temperature outside. Turns out that particularly cold and particularly hot temperatures reduce participation in recreational physical activity. So there are physiological potential effects of climate change there. A number of economists more recently have begun to look at the effect of exposure to heat stress on our cognitive performance. So if we're fatigued physiologically, does our cognitive performance also decline? And they found across a number of studies that it does. One of these studies, for example, uses large-scale SAT data to try and identify the effect of temperature on it. And a number of different disciplines, from criminology to psychology to political science, have found increases in violence as well as discontent and aggression as a function of temperature. What is emerging from this discipline is the notion that there is kind of an ideal temperature for human well-being, and towards the extremes of the temperatures, humans don't do as well. So that's just kind of the big qualitative where the literature is at that we're working. And why we're here today is because we were wondering what other social variables might be affected by temperature. And more specifically, could weather alter emotional states?
Did you consider mostly temperature or also humidity and other?
Well, we consider all of the meteorological variables because we'll talk more about that. I will get into the methods of all of this estimation. I know you're all hungry for the actual methods details.
Temperature or deviation from the gathering?
Fantastic question. I will walk right through that. So the basic question is emotions and weather. And it kind of seems that our experience suggests that perhaps our emotional states are indeed affected by the weather. We were talking about that with the person who set up I was talking about that with the person who set up the technology here, talking about the weather, talking about living in different places, exposure to weather, and how that makes us feel. It's something that we talk about and we think about. And it's been something we talk about and we think about for literally thousands of years. And there are lots and lots of studies that have in some way mentioned this concept. So we figured that it would be really difficult to address, potentially, that there would be no easy and quick solutions. But then we came across these things called mood rings. And I don't know if you've ever seen mood rings, but they're these children's toys that you put on your ring, and it's a function of your body temperature. It tells you exactly the mood that you're in. We discovered that, gave us the answer. So thank you for coming today. The rest of the talk is over. No, it's not easy. And the more we dug into it, the more we realized that it was hard. And as a result, the empirical evidence in the literature is quite mixed up. There were a number of small-scale studies done by social psychologists initially, where they would take small groups of students, and it would be a sunny day, and they would make them go outside, and it would be a sunny, pleasant day, and then they would make them go outside when it was a cloudy day, kind of unpleasant outside. They took these groups of 30 students and said, wow, look, huge effect size. So weather matters a ton. There were a lot of initial studies like that. They suffer from likely file drawer bias, as well as what's called type M error, which is more likely to actually see published large effect sizes from small samples. And then subsequently, researchers said, okay, well, we'll bring larger and larger data sets to bear on this question, sometimes correlational methods, and those findings were mixed, and they were also somewhat subject or somewhat fragile to the specification. And so when we got to this question, there was really no conclusive evidence. And we thought, okay, well, we're good with social media data. We have lots of social media data, and we know how to work with these large corpus. So maybe we should just bring to bear the largest text-based corpus that has ever been brought to bear to answer this question. And that's what we did. We took over 2 billion Facebook status updates from 2009 to 2012, and over 1 billion geolocated tweets from 2014 to 2016. And that comprises the corpus that we're working with. For the purposes of this analysis, when I'm talking here, we aggregated these data to 75 largest metropolitan areas. In order to talk about emotion, we need to talk about emotion. And when you want to talk about emotion, you go into the field of what's called affective science. And affective science is a science designed to both theorize and measure human emotions. And it's a lot harder than you think. That's kind of one of the surprising things that I got into when I got into this. Emotion theorists don't even agree whether emotions are discrete or continuous experience. They don't agree whether or not there is such a thing as an emotion or a spectrum of emotion. And if it is discrete, if you do think you can have discrete emotional experiences, how many are there? And what are they? And how much does that comport in one population to another population? So there are a lot of outstanding questions. We don't answer them. I'm not an affective scientist. But what we do is we do what is common in affective sciences to say, we don't know exactly how many discrete emotions there are, so we're going to distill them down into 2 dimensions that we're going to call positive and negative affect. And positive and negative affect are treated as 2 distinct dimensions because you can kind of experience both at the same time. You can be a little bit happy and a little bit sad about certain events in the world. So that's why social psychologists and emotion theorists treat them differently. So that's what we're going to deal with here. And then in order to measure positive and negative affect, we need to classify our linguistic expressions in some way. For the purposes of this study, we use 3 common sentiment classifiers classifying positive and negative sentiment. We use Luke, senti-strength, and the Hadometer. The key point here is the results that we get from using these different classifiers look very similar across classifier. I'm going to present the Luke results here just for the purpose of simplicity, but in the actual paper, which is coming out tomorrow, you will see all of the results and they all replicate across these classifiers. Now, once we have positive and negative sentiment classified for this huge corpus of text, we want to merge in our meteorological variables, precipitation and temperature. And it's the next slide. And so what we have is maximum temperature in degrees Celsius on the left, some total precipitation on the right. And you can see they vary across our cities, across the time periods that we have for our data. We do want to include other meteorological variables. We include diurnal temperature range, relative humidity, and cloud cover. We also look at specifications of various interactions of these, because if you don't control for other meteorological variables in your ultimate analyses, then they can confound your estimates of temperature, because these things correlate with temperature. All right, so now we have the data, and we have our sentiment data, and we have our meteorological data. How do we put them together in a way that gives us the question that, or the answer to the question that we're interested in? Can we just take the data? So on the y-axis here is the level of positive sentiment in percentage. And on the x-axis is maximum temperature in degrees Celsius. And this is, each point represents a city day in the analysis. This is all the city days that we have for the Facebook data. The black line is just a simple linear fit. And the orange dots represent non-parametric smoothing of the data, taking a mean positive sentiment for each 5-degree temperature. So what you would derive from looking at this is it looks like there's a slight positive slope associated with warmer temperatures and positive sentiment. Warmer temperatures produce higher rates of positive sentiment. And you might even also say, well, it looks like from the orange dots that cold temperatures maybe reduce positive sentiment as compared to others. And if you did that, this is very common and done in a lot of the historical studies, if you just did this, you might be making erroneous inferences. And the reason you'd be making erroneous inferences is because these are just raw levels of observational data. And when you're dealing with raw levels of observational data, you have concerns about spurious correlation. There could be spurious correlation with secular trends. There could be spurious correlation with variables that vary seasonally, much in the same way as temperature varies seasonally. There could be some forms of selection in the data, whereby people select into living in certain places that have certain meteorological distributions, not necessarily because of those meteorological distributions, but because of some other feature of the city that is fixed and correlated with those meteorological. So you have all kinds of potential confounds in the data, such that if you just look at a simple bivariate correlation, you don't have causation. And that is, I'm not telling you anything new here, we hear this all the time. Correlation is not causation. It doesn't imply causation. But sometimes, if you're careful with the data, it can indeed imply causation. Yeah, go ahead.
Quick question. So you're talking about confounding variables from other weather phenomena.
Sure.
What about confounding variables from other factors like SES?
Great question. So I'll talk about that at the very end. I'll table that, and then I have a slide that we can go to and talk about that. The answer to that is a more statistical question. So the key point is, if you're careful with the data, sometimes you can back out causation from an observational correlation. And that is the crux of the field that I'm engaged in, which is econometrics broadly, but climate econometrics. And this field attempts to uncover causal inference from observational climate data and observational social outcomes. And how do you do that? Specifically with respect to this, what's the causal effect of weather on sentiment? Well, one way you could think about this question, take a step back, is what would be the ideal experiment that we would run in order to answer this question? And if we were omnipotent, what we might like to do is just control the weather. And if we did that, we could take the 75 cities in our analysis, one group, randomly sample them into subgroups. So now they're balanced in expectation. And we can take one group and we say, okay, you have hot temperature. We take another group and we say, you have mild temperature. And then we measure the positive sentiment for those two groups and look at the mean difference between positive sentiment between those two groups. And we now have a causal estimate. We've designed a causal estimate such that we can know the effect of hot temperatures as compared to mild temperatures. Now, we're not omnipotent, unfortunately, or fortunately, depending on how you think about it, so we can't run this experiment. But we can get close to it with the observational data if we're careful. We can observe temperature over time within the same location. And then what we can do is we can deconvolve potential confounds from the data. I'll talk about what this process is and I'll walk us through it. And then the remaining variation in temperature we can treat as exogenous to our social outcomes, occurring outside of our social outcomes. Then if we compare outcomes correlation with the unusual temperature or the remaining variation in temperature, that can give us an estimate of the causal effect. In this setting, the correlation is a causal estimate. What does this mean conceptually? So if we think about this very kind of simply, is today a little bit warmer or a little bit cooler than normal? This gets here. Is today a little bit warmer or a little bit cooler than we would expect? We'll call that a temperature anomaly. If it's epsilon warmer or epsilon cooler, that's the kind of variation we're interested in. This is the variation in the data, in the Facebook data for Columbus, Ohio, where I was born, so that's why I chose it. And as you can see in the left panel, which is temperature on the y-axis and date on the x-axis. Sorry, I know this is a little bit small if you can't see it in the back. You can see that temperature has clear seasonality to it. Columbus, Ohio has seasons. Not quite like LA. And in the right panel, you have positive sentiment in percentage points on the y-axis and date again on the x-axis. And you can kind of see that there's somewhat of a positive secular trend over the course of our Facebook data in positive sentiment. And in both series, there is inter-day variation, there's inter-week variation. As I mentioned for the temperature data, there's seasonal variation. One thing you might want to do to remove one potential confound is to say, okay, we're worried about things that are fixed at the city level. For the purposes of our analysis, a place's climate is fixed as well as their institutions, their culture, and maybe we want to pull these things out so we don't get some potential confounding from there. In the way you do that is you would include what are called city level fixed effects or fixed effects. They're indicated variables. And effectively what they do is they demean the series around just the city level mean. And so you see that in orange. But as you can see in orange, there's still seasonality in the temperature data. And so there's still potential for seasonal confounds to bias our inference.
The mean is across all time?
The mean is across all time in the series, yeah, per place. So you can see that there's still seasonality in the orange series, and you'd like to pull that out so you can pull out potential seasonal conflict. And the way that you can do that is you can include city by month as well as date-specific, idiosyncratic, date-specific fixed effects. And what you're left then is in purple. You can see it pulls out the seasonality, it pulls out the secular trending, it pulls out the fixed mean. And this series then, if you zoom in, gives us conceptually the anomaly space. It tells us whether today is a little bit warmer or a little bit cooler than we were expecting. And it also tells us whether today's sentiment was a little bit higher or a little bit lower than normal. So we have these anomalies. These now give us our causal inference. So we think once we've deconvolved most of the potential conflict, that remaining variation in temperature is then as good as randomly assigned, because we don't control, as I mentioned, we don't control the meteorological system. It's as good as randomly assigned to us on any given day. And that gives us then a natural experiment that we can leverage to derive causal inference. So now we have the deconvolved data. On the x-axis is the maximum temperature anomaly in degrees Celsius. On the y-axis is positive sentiment anomaly, percentage points. Yeah, go ahead.
Why does this make sense? If it's 90 degrees and it's warmer than normal, that sucks. And if it's 40 degrees and it's warmer than normal,
What a
that's great.
fantastic point. Thank you for making that. So, that's literally the next slide. So what we have here is a bivariate correlation. And we say, okay, we're looking at the maximum temperature anomalies across all the data that we have. And you can see a positive trend that on average, it being a little bit warmer than usual tends to be good for positive sentiment. It makes positive sentiment go up a little bit on average. But exactly that point, it's not the case that we would expect theoretically that maximum temperature anomalies should have homogeneous effects across the level of the temperature distribution, right? They should have heterogeneous effects depending on whether it's 90 degrees or 32 degrees. In order to back out that, in order to do some other statistical things, we do put this into a model. And I'm happy to talk about this with anyone who's interested in nerding out on the empirics like I am. But again, the dependent variables are rate of positive sentiment, rate of negative sentiment, independent variables, maximum temperature, precipitation, cloud cover, humidity, temperature range. The unit of analysis is the city day. We have the fixed effects that I talked about that allow for the deconvolution of the data. We use semi-parametric bins to model Tmax. We provide ranges we break maximum temperatures into ranges. And then we treat our standard errors in a way that clusters on city as well as date to deal with potential serial autocorrelation and spatial autocorrelation on each day. And we weight the regression by the number of posts in each city. So that's the model. We can talk about that more. And what that produces for us then are estimates that give us marginal effects across the level of the distribution, leveraging anomalies in each space. So this is the Facebook data. And what we see is indeed exactly what you would expect to see. We see that for particularly cold temperatures on the left-hand panel, you have reductions in positive sentiment, which is in orange, up to kind of ideal temperature, 20 to 25 degrees Celsius, 65 to 75 degrees Fahrenheit. Beyond that point, positive sentiment declines. Negative sentiment increases at hot temperatures and also increases at cold temperatures. We see in the right-hand panel that precipitation pretty much linearly worsens sentiment. So that's the Facebook data. And then the Twitter data. The Twitter data produce a functional form that looks very similar in terms of its general functional form. The effect sizes are somewhat reduced. We think that that is due to the fact that the measures of sentiment we have for the Twitter data are a little bit noisier. Expressions are shorter, and people are talking publicly as opposed to their social networks. So the data that we had, we observed kind of different levels of affective expression across the platforms. But the functional forms are very similar. So let's talk about what it is that we're actually doing here in order to translate the model results into the conceptual space that I provided with the anomaly and the actual raw data. What you see, if you pull just the positive sentiment from the Facebook result, this is from the model in the top panel. I don't know if you can see this in the back, but basically what you see is if you treat each temperature range as its own separate range, and you look on the x-axis at the maximum temperature anomaly in that range and the positive sentiment anomaly, you can see that around freezing, when it is unusually warmer but otherwise supposed to be expected be around freezing, you have this substantial linear positive slope. It's good. It's good to be warmer when it's cold. But when you go to the hot end of the distribution, you go out to 35, 40 degrees Celsius, 100 degrees Fahrenheit, when it's unusually warm out of that end of the distribution, that causally reduces temperature. So that's what's going on in the model. The model also allows us to get the parameter estimates for the effect of the other variables, other meteorological variables as well. It seems that cloud cover, humidity, both worsen sentiment, and diurnal temperature range, reductions in diurnal temperature range also harm sentiment. And we think that's likely due to the fact that typically nighttime temperatures are warmer than usual when the diurnal temperature range is lower. And so we think maybe that is something that's operating through sleep. We don't know. That's a little bit of speculation on the causal mechanisms on that. So what we're left with then is that adverse weather decreases positive sentiment and increases negative sentiment. And at below freezing temperatures, decreased positive sentiment by approximately 1 percentage point relative to ideal temperature. And if you're kind of thinking about that, 1 percentage point seems a bit small. A wonderfully ideal temperature day outside compared to freezing temperatures produces a change in sentiment in these data of about 1%. That to me would be like effectively imperceptible. Why is that the case? Well, it's the case because of there being a trade-off in this method. And the trade-off is if we're deconvolving a lot of the potential signal out of the data, what we're doing is removing variation that could potentially be confounded variation. And when we do that, we're not removing noise. So the noise to signal ratio of the data increases. And as a result of that, the effect sizes that we're estimating decrease. So there's this trade-off. How can we see then whether or not temperature actually matters to the social system? We can compare the temperature effect sizes to the effect sizes of other events that occur during the course of our data that we would expect should theoretically reduce, for example, positive sentiment. And so that's what we did. On the left is the effect size of being below freezing as compared to ideal temperature. And along the right panel, we looked at a number of events that we specified a priori that we thought, okay, these occurred during our sample. Maybe they had a negative effect on sentiment. How large was it? And so from left to right, we have, in the gray bars, we have northern cities' daylight savings times ends, which is about half the size of the effect of being below freezing. We also have the anniversary dates of New York City in New York City, that effect on sentiment. The San Bernardino terrorist attack, 2015 in San Bernardino, what was the effect of that on San Bernardino residents' expressed sentiment? We also have the flooding of the Carolinas in 2015, as well as the San Francisco Bay Area earthquake. And what you can see here is that the effect size that we estimate for below freezing temperatures is in the ballpark of the effects of other events that we would think, yeah, that actually probably did matter. We did think for sentiment. So it looks like it's at least socially meaningful, maybe larger than just a 1 percentage point absolute inception. All right, so there are very many empiricists in the audience, as I can tell. They've probably had questions relating to robustness. They've already asked some of them. One of the things you might have kind of copy on or concerned about is that I went very quickly from talking about this huge corpus of individuals who were posting about their daily lives, and then I quickly aggregated them to the city level. I ran a bunch of city level analyses. And the concern there would be that the effect sizes that we recover at the city level are aggregates, they're averages across a bunch of different people, and so maybe there's a lot of heterogeneity at the individual level. And so maybe these results don't look at all the same if you're not looking at it. Moving this down to the individual level and using individual level fixed effects, we recover much the same functional form. So that assuages our concern a little bit there. The other thing that you might be concerned about is more of a measurement concern. And this is definitely something to be concerned about, which is if it's hot, really hot outside, unusually warm outside, or unusually cold outside, I'm much more likely to talk about the weather. And when I talk about the weather, I use linguistic expressions that have affect. The weather sure is crappy outside. Wow, what a beautifully gorgeous day. Those lexical expressions contain sentiment, but they may be not at all proxies for what I'm feeling at that point in time. So if you include weather-related speech in the analysis, maybe that's actually just driving the whole effect. So what we did is we built a classifier for weather terms, and we excluded them from the analysis. So we tried to exclude everything that was potentially talking about the weather, and we still uncover effects that look very similar to it. So we don't think it's just people talking about the weather, but in fact, if the weather is anomalous at different levels of the temperature distribution, it actually affects the sentiment that people are expressing, not related to the weather. The other thing I did here is I pulled a little bit of a sleight of hand from a measurement perspective. I went quickly from discussing positive and negative affect and emotions, to saying we're measuring sentiment, and now sentiment is our proxy for emotional. But no one's actually established ever that sentiment of social media texts is a highly valid proxy for underlying constructs of emotion. And what that means is, when I'm talking on social media, is that at all correlated with how I'm feeling? And there's a lot of reasons why it might not be. Most of our public posting is public. For Twitter, it's fully public. And for the Facebook data, it's public to our social media. So we could very easily censor the way that we talk in a way that doesn't allow for the recovery of underlying emotional state. We might be creating personas, or we might just have ways of talking that includes sentiment terms, but that are just largely orthogonal on average to the way that people are feeling. I don't think that that's necessarily the case. I do think it's probably a fairly valid proxy, but no one's established that. So that's what we're trying to do, because it is an empirical question. And so how would you do that? Well, you would try, ideally, to get someone to rate their own feelings. How are you feeling right now? Literally right as, or right after, they posted a post on social media. So we built out a botnet, and we also have an app that we're trying to do exactly that. We're trying to get you, and if you would like to, it's called Deepmoji, if you'd like to go help us out. We're trying to get people to, for their most recent social media post, tell us how they felt at that moment. Not how they think their post would make other people think that they felt, etc., but actually just how they felt. And there's a lot of posting that might give us some features about underlying emotional states that a third-party rating of the lexical expression might not. So if you think back through all your tweets on Twitter, you might post, for example, a question about a Stack Overflow related question to Twitter, or a question about programming on Twitter, when you've been struggling with a piece of code and you're frustrated. But the way that you write the question is just, I'm curious about how to program this thing. That wouldn't get picked up on a sentiment classifier. But it might actually be a signal of potential underlying. So there's a lot you can do with that. This is something that we're trying. The final thing is we're dealing with social media data. And so anytime I give a talk on social media data, somebody raises their hand and says, my grandmother doesn't use social media. Is this generalizable to the population more broadly? It's a great question. It's an important question. We as social scientists want to know how people, broadly conceived, representatively, behave and are affected, in this case, by meteorological conditions. Facebook data that we have, 2009 and 2012, that's all status updates on the platform. So it's representative of whoever was using Facebook at that time. That was a smaller and less representative sample than Facebook users are today, but it was a good cross-section of people. People who geolocate their tweets are weird. People who use Twitter are weird. People who geolocate their tweets on Twitter are even weird as compared to Twitter users. So I don't really know that that geolocated tweets are at all generalized. But one way to get at this would to say, okay, well, we have social media from the US context here. Other people post on social media, other places around the world. What might you see if you did this analysis outside the United States? So what I did with some other colleagues is get data from Weibo on Chinese expressions. And we used classifiers to classify the sentiment of those and uncover a very similar function of one. So it holds in multiple contexts. That doesn't necessarily mean this applies to people who don't use Weibo in China, but at least there's some convergent validity on the
Is, I mean, just can't say if it's, it looks like, the mean is more significant than US, so there's like stronger effect.
The effects are a little bit larger in that data. The data are also, the estimates are a little bit noisier as well. So. Okay, so just a brief summary. What we have is that whether causally alters sentiment in a sample that adverse weather harms sentiment, mild weather augments it. The effects are kind of socially meaningful in comparison to other effects, and still, as all projects in the empirical world, more remains to be done to convince everyone who's an extreme skeptic this is actually what's going on. I want to talk about climate a little bit because I started talking. Why am I doing this project? Well, I'm kind of interested in what happens when you change the temperature distribution in the future and people are no longer exposed to the meteorological conditions they've been accustomed to. How might climate change impact emotion? Now, in order to talk through this, I'm making a very strong assumption. That assumption is if no adaptation. I'll talk about that in a second. It's a very strong, probably wrong assumption. But if there is no adaptation, or mild adaptation, if there is no adaptation, then places that are very cold in the winter, you might expect to see, on average, improvements in sentiment. Places that are very hot in the summer, you might expect to see, on average, worsening. There's a kind of a key point here that relates to these climate impacts estimates, which is the uncertainty around forecasts for future precipitation and especially cloud cover and relative humidity at the location level the uncertainty is very high. So it's really hard to say what those meteorological variables changes might be in the future and as a result of the social impact of that. So the next step actually is to try and answer whether or not that assumption and how reasonable it is to make that assumption. Because I moved to Boston from San Diego, and initially, the first winter there, it was terrible. It was really cold. I was like, wow, I want to be back in San Diego. Second winter, it was just as cold, but I had bought the proper clothing, which I didn't think to do the first time around, and I was exposed to these temperatures more regularly and kind of came to know what to expect. And as a result, I would say, from my own subjective experience, that I did adapt somewhat to the meteorological conditions I'm now exposed to. So how much does that occur in the population, and how costlessly can people adapt, and at what rate will they adapt? We're asking a number of questions related to this. We're also asking questions related to expectations about the weather, which we can talk about as well. And I'm also interested in a number of other questions that relate to estimating the social impacts of climate change. But if you think that emotions might be affected by meteorological conditions, and conceptually that emotions might affect the degree to which we engage with other people, does that actually alter does the changing or do extreme meteorological conditions alter our propensity to communicate with other people? Do they alter the forms that we communicate with other people? Are we more or less likely to spend face-to-face time with them? Are we more or less likely to be on social media in the first place? And then secondly, if that is the case, or if there are these changes in communication patterns and potentially changes in ties over time, does that dynamically alter, in some sort of cumulative sense, the structure of our social network? So those are a couple of other questions that I'm working on. Thank you for your great questions and your time, and I look forward to more of your questions.
I want to play the reason why I'm going to do that is because I believe you, because at least I have half a dozen papers on sentiment, information diffusion, and contagion of sentiment, all these sorts of things. So we're talking the same language. But for what concerns the methodological, I have a tons of questions, but I'm going to ask two for the sake of time. So one is about indeed contagion, and I'm surprised you didn't talk about, or maybe you didn't look at that, or you didn't talk about it because James has a lot of work on that. But and the second thing is confounded. I'm going to start with. So in the early on when you talked about sort of the methodologies to address confounding factors, etc., I was thinking in my mind that maybe there are other factors that you're not capturing when you're factoring out the all the additional variables that your model accounts for, and then kind of goes to the just looking at the anomalies, right? So, for example, if you're a kid and you go to school, you're probably less happy than on holidays when you don't go to school, and or in the summer, sometimes most of the kids, right? Or in the summer when it's holiday and so on. So and the same for adults. So like if you go to work, that during the workday you are less happy, and during the weekend you're happy. There are external factors that are social in nature that are endogenous to the system that you are polling but are not at all reflected in any of the sort of environmental exogenous variables that you are, factoring out through your model. So do you have any thoughts on how those dynamics of the social systems can affect the mood or emotions that you measure but you don't observe?
Right. There are two answers to that. That's the first question. There are two answers to that. One is, so let's use the example of school days. We are controlling. So we have day-specific fixed effects. Right? Because in the United States, school days and work weeks are exactly the same, we are controlling for the fact that you may or may not be at school if you're a child on that day. And so any other confounds that we would want to think about as being potentially concerning here need to vary in a way that that doesn't vary date idiosyncratically as well as city by month. And so things like that, it's hard to come up with confounds that would co-vary with the series that I showed. It would need to pretty well co-vary with that series in some systematic way. And it's difficult. The reason why we are comfortable making this assumption is it's very difficult to think about things in the social system that systematically co-vary in that way that are not actually caused by temperature. And that latter point is really important because when you are doing estimates in causal inference, if you include what are called post-treatment covariates in your regression, so say for example, you give education credits to children and you want to measure their test scores. And those education credits, they actually offset the budget constraints for these children. So the children eat better. And you include the increase in nutrition of those children in your regression. What that does is it gives you a biased estimate because now that variable is correlated with your treatment, it biases. So anything here that is potentially correlated with the remaining meteorological variation that we have, that is in any way potentially caused by that variation, which are very many features, we actually can't include in the regression as controls because that's going to systematically bias the average treatment effects that we're estimating. So those are kind of the two ways that we think about that question. Very good question. And then the second question is fill in the network. And there's two answers to that. One is we don't look at it. And two, we should. And the reason that we should, the reason that we don't is it's very common in the econometrics literature to make what's called the Sutva assumption in causal inference, single unit treatment value assumption. And this assumption is almost always violated, but it's something that most econometricians and economists typically don't pay a lot of attention to. But here, in many situations, social situations, you should estimate that because there could be spillover. For example, if it is the case that there was as Lorenzo and James showed in a separate paper, if there was a very rainy day in New York City and you had friends via your social network that were in Arizona, then there is some, though small, but some contagion of those effects throughout. And so in that way, if you think that there are large positive or negative spillover in these data, that could potentially bias these estimates. What I'm interested in doing is taking that idea and kind of turning it on its head to see, given that we've been estimating all of the effects of climate change, not just in social systems, but also in natural systems, can we look at, and that's what kind of the communications and social networks data, can we look at the ways that we might be systematically underestimating or overestimating the cost of climate change in the future? Because ecologists, biologists, ecosystem specialists, they oftentimes make the Sutphin assumption. So those are great questions.
Very 30-second follow-up, and then I let everyone else. The first thing is, thanks for the clarifications. I think I understand your point. The comment is you're looking at network systems, social systems. I think looking at network effects is due.
Totally. We are agreed on that.
And the second thing, as you were explaining that, I was thinking about ways I would have done it. So alternatives and probably not as good, but a possible idea, and maybe then the future we write a paper about it, is people relocate all the time from place to place. You can use, interrupted time series type of analysis and do a pre-post natural experiment of people who.
That's a good idea, and we've thought about doing that. The challenge with the inference there is people always move for a reason. And it is the case, for example, that if I were to move to Southern California, moving to Southern California for its climate would actually, and for the meteorological distribution it has, would actually be part of that selection equation. And it's difficult to tease out If I'm selecting into living in a place, and that place, once I move there, my emotion is better. Is it because I like that, or because that's causally affected? Or because of some other factor that is associated with the fact that I moved? So it's a hard causal problem, but it is, I think you're very much right, thinking that for people who are moving due to exogenous reasons, say for example, there's a mass labor shock in one part of the country, and you can trace, or Katrina, for example. Katrina caused huge pushes, a pulse of people to move all across the country. If you can track those individuals, then you should theoretically be able to say, okay, we think that because these people were budget constrained and they could only move so far, they probably didn't just move to Oklahoma because they loved Oklahoma. So what's the effect of moving to Oklahoma as compared to being? So that's a really great question as well.
And you get control for, socio-demographics.
Yeah, you can,
and
you can try to
economic
control for
factors.
as many of the observed variables. The concern is there's always some unobserved heterogeneity.
But if you move to, California, the weather is better, but it costs more money than
That's right.
Oklahoma,
That's
right? So there are things that demographics and other things that you can account, and you can decide whether
Yes,
they will affect or not.
The hardest part is to partial out the selection, and really to be sure that it's not the selection that's driving it. Yeah, that's a really good idea.
I have a couple of observations and questions. Could you explain again why you think that any variable that is systematically correlated with temperature might not give affect results? For example, if there's I'm not talking about just natural disasters, but like power outages, if they're systematically associated with
So
warmer than
if temperature causes
something else that affects the emotional state, how can you rule those things out?
So this is this is not an easy question statistically, and it's actually something that until probably the last 2 years, economists and econometricians weren't paying much attention to. But in most recent working papers, we're paying a lot of attention to, and that is if it is the case that your electrical grid is affected by a temperature shock, and it's because high temperatures increase electricity demand and your grid can't handle that, and so you have brownouts, then there is a partial correlation between the remaining variation in temperature and your changes in your electrical grid. And if you then put both temperature and changes in the electrical grid into a context of a regression, you now have covariance between your treatment variable and one of your controls. And the whole strength of regression is the idea that it is in expectation uncorrelated with all the remaining variables. And so now when you have that covariance, you have a complex structure in a multiple regression framework. You have a complex covariance structure, and your parameter estimates for your treatment depend in some way on the parameter estimates for, in this case, the changes in your electricity. And so you will have a systematic bias. And the difficulty with this type of bias is, and people have done proofs on this, that it is unsignable and of potentially infinite magnitude. And so it really messes up the estimation of the causal parameters if you're including things that you think are post-treatment covariates. This is like 3 years ago, I wasn't aware of this being a problem, but now it is.
Now I am. One more observation, actually. So you measured just sentiment, for example, but you did similar studies actually measured this actually very strong effect on arousal. Arousal would be a very interesting thing to measure, and it directly relates like violence and some other. So the strength of the emotions, I would predict that you might even have a stronger effect.
Yes. Yeah. I mean, so arousal gets very close to the boundary between physiological effects and emotional effects, and it's kind of, if you measure, for example, increased cortisol levels in the blood as a measure of heightened arousal, that is something actually just that I'm very interested in trying to do. The difficulty is arousal, trying to measure the psychological construct of arousal as it is some sort of proxy for heightened emotional states is just as difficult as measuring emotion. And it's from a subjective standpoint, it's very difficult to get good, reliable metrics of what it means for someone to say that they are aroused. Because really, in the way that we subjectively interpret our experience, that could mean I feel jittery, I feel kind of frustrated, but we always layer some form of psychological subjectivity on top of the interpretation of physiological arousal. And so that's where like blood measures would be great, but we
Sure.
don't have data on the measure.
Sure, but there are instruments like, the WKB lexicon, for example, measures both valence, which is the same as the sentiment, and arousal as well. So
The
as far as
intensity of this.
intensity
Yeah,
of the
okay.
expressor, as far as you can trust sentiment as a proxy for emotional state, you can trust this arousal as a proxy for high.
I really think there's something to that. And one of the ways we thought of doing that, since we have the actigraph data, and actigraph data tracks your heart rate, is actually to use heart rate as a proxy for physiological arousal, especially kind of quick peaks and then subsequent returns. If someone's working out, you're going to see that they're working out, so it's going to be elevated heart rate for time. But there might be ways to partial out from observational data actual physiological arousal, and then you don't have to worry so much about the measurement standpoint of what people are actually subjectively experiencing when they have arousal in some way. But that's a very good.
So, just a quick question about perhaps the kind of conclusions that one draws from the work that you're talking about.
Sure.
So, I mean, just at a very superficial level, one might say, okay, people who are in very, very cold places are kind of less happy than people in moderate temperate places. I mean, I'm worried that I might be oversimplifying things, but if that's the case, then I mean, is that what you're saying? And if so, are we in Southern California a lot happier than people who are living in Minnesota? And it's just a reason why people who live in Norway have high suicide rates.
That question is at the core of this. Because what we would like to do conceptually is just say, the Earth is going to be 3 degrees warmer in the future. And so we can literally actually just say that a climate distribution, not the variance around that distribution, not the meteorological realizations of that distribution, but a climate distribution, it's cold in Minnesota. That causes them to be less happy than it's hot in San Diego. But the problem is, you can't do what we did here, which is partial out all that variation, because relatively, for the most part, those climate distributions are fixed. And so I can't say, I would like to be able to say, but there's no good statistical way that we've been able to find to be able to say that it's conclusively the case that because the climate distribution is colder in Montana or Minnesota than it is in Southern California, that is the thing that causes. I can tell you that in colder places, when it is unusually cold, that harms sentiment. But that may just be because they want it to be just this amount of cold, and beyond, like a little bit colder than that is not good. And so it's actually, it's a really good question.
But this climate change is going to increase the variance of.
Theoretically, yes. So far, we actually haven't observed substantial changes in the second one. And there's a lot of empirical work kind of scratching its head about when is this going to happen. If that does happen,
So I have, for the most part, a trivial question about the sleep.
Sleep
Study that you mentioned, but you didn't go into the specifics, and this might sound stupid, but differently from this overall analysis that accounts for any situation during sort of the course of the day for for these individuals. For the most part, most people sleep in their bedrooms, and you can assume that for the most part, most people have controlled temperature in their bedroom because they might have AC or whatever, right?
Sure.
Or heating in their absence. So how do you relate external weather temperature to sleep quality? Do you have access to environmental sensors like humidity or temperature of the room? Or
so that's a very good question. The sleep research experts asked the same question. These things.
I'm not a sleep research expert, but this is
Apparently
based on
No, that's a great question. So how many people in here in Southern have, or even in the spring in Southern California, use air conditioning or heating?
in the winter?
Either. Like, how frequently is it the case that you're using heating or cooling in Southern California? Sometimes, but sometimes you don't. And it's the case in San Diego as well, that a lot of people don't really have have any sort of, especially central AC. And a lot of people that I know in talking about this have kind of reported this, like, oh yeah, during the winter we like to leave the window a little bit cracked, or we don't really turn on the heat or the cooling, but it kind of cools down to a comfortable temperature in our rooms. We have an appropriate amount of bedding on the bed set because, for the most part, temperatures in February in Southern California are pretty consistent. And so what we think is the case, though I haven't proved this yet, but what we think is the case is that it is certainly the case that people adapt to the sleeping conditions for that season, for that place. But then once you have this variation around that, if it's 10 degrees Celsius warmer at night than it's supposed to be in February here, or even 5 degrees Celsius warmer, you might have a number of blankets on the bed that is just enough that it takes you out of your circadian rhythm at some point in the night, such that you have to pull off an extra blanket. And so we observe these effects, even though it's the case that people have adapted to the climates and the places that they live pretty well. With blankets and cooling and heating, we still observe the effects. And so what that means is, it is the case that in some way, outside nighttime temperatures are influencing the way that you sleep. And we'd probably have a lot better estimate if we actually were able to measure indoor air temperature. So for example, we got smart thermostat data, and we could link that with actigraph data. You could answer that question. The problem is, no one had actually done this before in the sleep research community, and the reason is they just rely very heavily on experiments in the lab. And if anyone's ever been into a sleep room or a sleep lab, the external validity of what you behave like or how you sleep in a sleep lab is very questionable with respect to how you would sleep in your own bed. So, and in fact, we know that when you aren't sleeping in your own bed, it causally changes the way that you sleep in your circadian rhythm as well. So, but that's, I mean, you say it's a simple question. That was the core question that a lot of sleep researchers were curious about. So,
I think this is all the time we have for questions.
Great questions. Thank you.
Let's thank the speakers.
They know where they are sleeping. Yes.